this old house. Yeah, this is an old house. My wife Chris and I lived over in Maine for 30 years, and then my son, I went to Mount Herman School in 1963 to 1966, back when it was Mount Herman and Northfield, of course, two separate schools. And it was a wonderful experience for me, so I wanted my son to go to Mount Herman again when he got old enough, and that was back in 2004. So we moved from Maine. He's our only son, and we didn't want to lose him too quick, so we came with him. And it was kind of interesting because when we used to live outside Boston, and when I'd come to school, we'd come up over the Gulf Road and come down Maple Street and go right past East Street. Little did I know that, 40 years later, I'd own a house on East Street. We looked for, when we decided to move over here, Chris started to look for houses on the internet, and this little house popped up, even though it wasn't listed yet. Somehow they buggered up the listing, and it all of a sudden came on their site before it was even listed. So we sort of got a little bit of a head start from other folks, and the picture just showed the house, and it showed a view out the back, and this property actually goes all the way up to the top there, all the way up to the top. There's 12 acres of land here, and we were coming from Maine, where we had 120 acres in Kennebunkport. So,
oh, nice.
Which was bought back in 1975 when land was cheap. So we came over here and did a tour of the house, and of course the house was a complete disaster. I mean, a complete mess. But it was a beautiful view. So it was like, okay. And of course, I don't mind working on houses. I've done it all my life. So I looked at it and I could see what the potential was for it. The history of the house, the central portion there, which is about 25 feet by about 15 feet wide, 10 feet high, which is amazing. That was one of the things too. When I walked in, the ceilings were 10 feet. I was like, wow, this is the type of ceiling I like. So I'm 6'4". And so that portion of the house was actually connected. It was an L on another larger house. And the house was originally located up in the Commons. Now, Northfield used to have a Commons. There were two roads, like in Hadley or in Hatfield. They have those two roads going north-south in one section of town. And there's a common down the middle. Northfield used to have a Commons. I think it was 1858, they decided to make it just a two-lane road and make the lawns big and wide on the houses rather than have the commons. And there were 8 houses in the commons, so they had to get all these houses out. This was one of them. It got split in two. One piece is down the other end of East Street, the larger piece, and this little piece got put down here. Now, when it was put here, East Street was just basically a little tiny lane, just one little dirt lane. And so the house was actually 30 feet that way. It was actually set on a foundation right up against the road. Back then, you had a cart going by, that was it. So it was literally about 6 or 7 feet from the road. When we bought the house, of course, I looked at that and said, this isn't going to work. Because first of all, you open the front door and you literally were stepping onto the street. Sometimes people come down this street awfully fast. It's a small, narrow little road, but people seem to think it's straight, I can go 100, so they just fly down this road sometimes. Not too often, but enough to give you that whoop sound as they go by the door, the open door. So I knew I was going to move the house. The foundation, of course, was the second impetus. The foundation was large field stone with a concrete cap under that section, a partial section under there of cement block, just rubble stone, flat little rubble stones all laid underneath this section for the foundation, and that section over there was basically on cement block, and it was so wet over there that you could punch your finger through the cement block. It had been in the water so long. The cement block will actually deteriorate if it's in a little bit of acidic water. It's like being in vinegar, it just slowly dissolves. So I said, well, okay, that's another good reason to move this house, because the foundation is just terrible. Again, some foundations are so bad that it just takes you incredible effort to make them good, and you have to have a good foundation under a house. I mean, if you don't have a good foundation, your house is going to be miserable forever. It's got to be dry, it's got to be warm, and it's got to be solid and airtight. So that's the critical part of a house is its foundation to begin with. So what we did, was I looked at the site, and obviously the house couldn't move too far because the house is, a big object. You can't really. And I've moved 7 different buildings, including a 32 by 64 barn, so I could see how to move things. But this was a little bit odd because it had all these additions. The main house, again, is 1790s or so. When they moved it, they put this little room on here, which was a little bedroom. By the way, this was a wall right here, and there was a doorway right there. So this was a bedroom that was put on once they moved it. There was a wall from that, right to the wall just to the left of the doorway there, came all the way and met this wall here, and made that a little living room. And the woman who was living here basically lived in that little kitchen area there. That's where she basically lived. So I'd knocked those walls out, obviously, and put in proper bracing and everything because I wanted to open the space up. But to move it to a new foundation, I said, okay, what are we going to do? Well, obviously, I'd love to have oriented it south. South is out this way. And I would have loved to have turned the house to face south. But that's quite a task to do. So I looked at the various aspects of the house and said, well, that is the Florida room, that's what she called it. So we might as well leave that down there. And we'll just move the house straight back. Also, it worked out better with the big maple trees behind here. There's 2 huge maple trees, sugar maples. And if we'd turned the house, we would have actually done quite a bit of damage to these trees. So I decided just to move it back. So to do the move, and again, this was all to get a good foundation. Like I said, that's where you've got to really put some of your effort is getting that foundation tight, and we'll talk more about that in a bit. So I took the house apart in the corners so I could make measurements. Old houses are not square. You can measure them on the outside, and they may be square, but they can be a parallelogram and stuff. So I had to basically make measurements under the entire house as to the shape of the structure, and I had to make the foundation match that structure. So the foundation, when they poured the footings, I said, this is the size of it, but it isn't going to be square. You're going to have to match my pins. So I put little pins in the foundation for how the house was going to be, foundation was actually going to be shaped. So like this room over here, we found out was 2 inches wider at that end than it was at this end. So I guess it was a Friday and they'd all had a beer or two before they started to finish the work. And the main house here, of course, was very much parallelogram. So we got the foundation poured, and then how were we going to move the house? And that's when I asked a fellow down here on, just over here on Captain Bears Plain Road. He does a lot of house setting, which is basically modular homes. It's Valley Crane from up in Brattleboro. And so I asked him about moving the house, and I said, can you use a crane to move it? I thought that would be, because I was looking at how to do it with timbers and stuff, and I was like, no, this isn't going to work going across that foundation. So they're going to lift it up. So he looked at it and he said, nah, it's too many things poking off the main structure. I said, oh, okay. So I sat down and tried to think more about it. A week later he comes back and he says, I think I can do it. I said, all right. So what we did was we literally put 2 huge slings under the main part of the house, that portion right there, which was also, this is all framed out in chestnut, which is a beautiful wood, very strong. Of course, we don't have chestnuts anymore. They're trying to grow ones that are disease resistant, but that whole frame is chestnut. Chestnut's like iron, so it was really a good solid structure. So we put 2 big slings around that portion of the house, and then he put a separate sling under this with a come-along, a separate sling under that, and a separate sling under that addition out over there. So there were 3 additions hung on with, actually used chain falls. And so the way that we lifted the house was he put the pressure on, there's a 1,000,000-ton crane, big crane. Yeah. And he basically lifted the main part of the house just enough to get it to have it come free of the foundation. And then he tensioned all 3 of these, so they just came off. So basically he ended up getting everything under the proper tension to lift all as one unit. So he lifted it up, swung it back, set it down, and we had 1 crack in the sheetrock on that portion of that, 1 small crack, and that was it. Pretty amazing. Yeah. So now the house had a foundation, and the foundation, of course, when I looked at the old foundation, I looked at the basement wall and I said, what's this big smudge mark along the foundation here? And the woman said, oh, that was 2 years ago when the sump pump failed, and that's where the water level rose to. And that's why they also had a new furnace, a hot air furnace. And I said, oh. So basically, that's where the water wants to be around here when it gets flooding. And I hate sump pumps because sump pumps always fail. So I said, well, okay, my footings are going to be at that level. So when we moved the house back, the foundation was only 4 feet deep. So the foundation underneath here is only about 4 feet deep. It's fully serviceable. I mean, I have a little scooter cart that I scoot around on when I want to do things. But the critical thing was that all the drains I put go to a gravity drain out there in the field. There's a crushed stone area where I brought the drain out to. So any water that comes in around the footings is going straight out there anyways, but the highest water level was still below the footings, so I've never had a drop in the basement, not even close. And when I poured it, I put 1.5 inches of foam under the slab, and then the walls have 2 inches of foam on the outside and on the inside. So it's basically an extremely well insulated basement that is, in the winter it runs about 58 degrees down there. There's no insulation in the floors here, so I let the heat go down there. But the basement is what's considered inside the thermal envelope. The thermal envelope of the house is basically the insulation layer, and it should go all around the roof, down the walls, and all the way in through the foundation, down the walls and under the floor. You should have the whole thing in the insulation envelope. It's the best way to do it. In this case here, where I actually use the basement, I have a heater down there, a hot water heater, things like that. So that's in the thermal envelope. And that's one big mistake that a lot of people make, is they don't include things like, they'll put a lot of newer houses, they'll put the big heating system in the attic so they can run all the ductwork for air conditioning and cooling, for air conditioning and heating. And of course, here's your heating system sitting in the attic with very little insulation over it, and it's like the worst place you could put it. It's outside of the thermal envelope, really. So not a good situation. All that heat is lost. So the basement in this house is part of the house. I can put a cardboard box on the floor and leave it there for a year or two and lift it up, and it's bone dry on the bottom. There is no mildew at all, period. So I don't have to run a dehumidifier all the time. I don't have to worry about a sump pump. It's completely benign, just beautiful space down there. So the house, once we got the house moved onto that, of course, now what do we do with the house? And the house itself had, again, this was one of these things where in many neighborhoods you'll find everybody's got the same vinyl siding, they got the same windows, they got the same roof sheet, shingles and stuff. A salesperson will have gone through the neighborhood and basically says, looks like you need new shingles. Hey, your siding looks pretty tired there. I think you need new siding. Oh, while we're at it, we'll put in some insulation. So this house had blown in rock wool. And rock wool is an insulation. Fiberglass is glass fiber. Rock wool is basically a rock slag and iron. It's a waste product that they can actually spin into a fiberglass. Roxol is the modern version of it. Roxol is, you can get it in bats, or you can get it in a material that you can blow in. But nowadays you don't find much rock wool being blown into spaces. It was an older technology. But that's what they did here. And so the house was, insulated a little bit. The problem with the house was that it was so leaky. This is not a big house, and she basically heated sort of one space with it. It used 750 gallons of oil for one winter's heating. So it was kind of leaky. And again, leaks come in the bottom and the leaks go out the top. And this had a lot of leaks in the bottom. I mean, the wind literally was blowing through the foundation over here. It was just blowing through because it was just those dry stones laid up. There was no chinking or anything in it. So it was like, wow, her bedroom must have been really cold in the winter to stand on it. It is just crazy. So the insulation was obviously inadequate. And of course, a lot of the sheet, this had a lot of, again, being a very old house, it was all horsehair plaster in here. The ceiling was kind of saggy, so I knew there were problems there. This addition over here, which I turned into a sitting room basically by taking out that wall, this had real problems with, again, there was no insulation in it really. So my first move was to basically gut out a lot of the interior of the house. And I started in the attic. Originally this house, again, being just a a house that was really, it wasn't really a house initially, it was more of a connector between the main house and a barn. And so it wasn't really set up. Upstairs was just like the typical, you come up the stairway and there was a bedroom and then there was another bedroom. They were just in a row. There was a chimney here too. There was a chimney for the hot air furnace. I took the hot air furnace out. That now resides up at a garage up here on the top of St. Mary's Street. The fellow's been using it. Saw him the other day. He said, hot air furnace is still working great. 10 years later, it's still working good to keep the garage warm. But there was an old chimney, and of course the chimney was one of those typical old chimneys that had 3 or 4 different holes poked into it, and it was all coming apart. So I just took the entire chimney down. I replaced it with a metal Bestus. You can see it's got a bag on it right there. I put a metal Bestus chimney in because I wanted to have a wood stove. And so that was my new chimney. And again, if you're ever thinking of putting a chimney in, don't put it in a masonry chimney, put it in a metal Bestus, one of the stainless steel chimneys. A lot less expensive, a lot more efficient. But we got the chimney out of the way, which of course freed up some space upstairs so that you didn't, because what happens, the door for the next bedroom was this little tiny door because it had to go by the chimney. So again, that 2 chimneys two bedrooms in a row doesn't really work that well. So what we did was we decided to make the upstairs, put a small bathroom upstairs, and have a bedroom, and just a little bit of a study space. We also realized the stairway, you can see the stairway now comes out underneath that window. The original stairway actually started on the right side of that window, and it basically made 1 or 2 winder steps and then went almost vertical up into the upstairs. So we basically made the best of what we had there by putting a few more steps, continued the winder. But now I think we added probably 4 steps to the stairway, so that actually gave me a good modest rise and a decent tread. You rise and tread, the formula typically is 17 inches. If you have 7 inches of rise, you want 10 inches of tread. If you have 6 inches of rise, you want 11 inches of tread. And it works out that it's just the average person's geometry. That type of a measurement gives you a very comfortable step. You will raise your foot and it'll be just where you want it when you raise it. If you have a different ratio, matter of fact, if you look at a step ladder, or a ladder like an extension ladder, the rungs are a certain distance apart, and if you put it against the house like you normally have it at an angle, you come out with that 17. The distance this way and the distance this way is 17. It's a very good number that works very well for your stairway design. So we got a much better stairway, and I put a nice handrail on it, so it's a safe stairway. But upstairs we put that bedroom on the end, put in a wall with a door, put in a little small bathroom with a shower, and had that little study area. So that was the layout up there. But of course the main problem was the rafters, especially in older houses. The rafters and the ceilings are really minimal. Again, way back when, wood wasn't exactly, you go down to the local store and buy what you want. It was milled out, and it was expensive, and sometimes you got wood that was reused. A lot of the wood in this building had been used somewhere else, and that was from 1790, so it was, parts from old houses get used in newer houses. Well, the newer house was 1790, so this had some parts in it. Some of the beams downstairs had mortises cut into it, so it was obviously part of another building at some point. And a lot of the boards had, one board I pulled off the house here had an advertisement for a circus or something on it. It was really kind of funny. But the upstairs had 5-inch deep rafters. They're like 4 by 5s. Well, 5 inches isn't a whole heck of a lot for insulation. So the first thing that I had to do is how are we going to figure out how we're going to get a little more insulation in that sloping roof. Again, this is what's called a raised cape, so the outside walls go 13 feet. And then there's a floor set in about 3 feet down, so your walls aren't knee walls that are set in, they're knee walls right at the outside edge. So it's a much better design because you don't have this problem of how do you insulate these weird areas that get cut out of a building. So the actual knee walls are the outside wall, and then the roof slopes up, and then you've got a ceiling. So the tricky part was how to get these sloping areas to have a decent R value, decent insulation value in them. And in this case, what we did was we built the 4 by 5 rafters down by simply adding pieces of 2 by 4 onto those sloping rafters to bring the depth in. And I blew that with cellulose insulation, so dense packed cellulose. We had about like probably 8 inches by the time we got done. So we had 8 inches of dense packed cellulose, and then I put another layer of 1.5 inch foam underneath that. So I had a foam board on the inside, the insulation, and then the sheetrock. It's not what I'd like to get. I'd like to have a ceiling. I really like to have R60 plus. And R60 is basically 18 inches of cellulose insulation. So we didn't come anywhere close to that, but it isn't a big area. So it's one of those little compromise areas. The attic I blew with about 14 inches of cellulose into the attic, so that gives me a good cap on top, plus 1 inch of foam. So we've got about close to R50, 55 in the ceilings, which is good. The wall areas, I used a very high density fiberglass. Fiberglass, if you look at fiberglass insulation, you can get it in the standard density, medium density, and high density. And if you look at the R values on them, you'll see the low densities are 11 for 3.5 inch walls, R11, R13, and R15. So the same insulation depth, you can get 11 or 15 if you really want to. So if you want to get a good insulation value on a wall, you get the high density. You have to order that stuff. They usually don't carry it. Mostly you can get R13 now right at like at Home Depot or something. Fiberglass insulation, it's a good insulation. I don't use it that much anymore, but it has to be really carefully fit. If you don't fit fiberglass insulation in a wall really carefully, it has about half its R value. So you want to make sure that if you're going to use fiberglass insulation, which has benefits that you can do a little bit at a time. You don't have to have a machine to do it or anything like that. With cellulose, you have to have a big blow machine. With fiberglass, you can just carefully cut it and put it in, and then next week you can come and do another bay or two. So that's convenient for the homeowner, but you've got to fit it carefully. So upstairs, I did use fiberglass, very carefully fit in all these various areas, and I put a layer of foam over it, again, to try and give me that depth, because I only have 3.5 inch walls up there. So I got a decent cap, and again, every time I did any finished work with the foam and things like that, everything was air sealed. Your house, 30% of your heat load can go out for heating the leaky air. So air leaks in the basement and goes out the attic, because in the wintertime your house is a big chimney. So that warm air gets sucked in at the bottom and goes out the top, and all that cold air coming in is going to get heated up, and that's typically around 30% of the average household's heating load. So that's a lot of wasted energy, and when you have an energy audit done by Mass Save or something, the first thing they'll do is come in and do air sealing. That's usually the first thing they recommend is air sealing, and it's usually the bottom, the rim joist around the basement. The rim joist is where the house sits on top of the foundation. That wooden structure there, it's called the rim joist, and the sill plate sits on top of the foundation. That's what they want to air seal downstairs. And then upstairs in the attic, they want to go upstairs and look at the floor and see where all those plumbing pipes come through and all the wires and the tops of walls. Any partition wall upstairs actually goes right up into the attic. Those are all spaces that can leak, so they want to go up there and air seal all that stuff. If you do that, you can cut it down quite dramatically. I was very careful in this house as I did it, and I got the air sealing to the point where I needed to bring fresh air in. Again, the house got so tight that literally it would get stale in here. It would get, the air would get really humid. So I did put in a ventilation system, which I'll show you later on when we're downstairs. But the insulation upstairs was done, and then we continued down doing these walls down here. I only did part of the walls down here. Actually, that wall over there, on the inside, it was unchanged. I never did touch that. That still got rock wool in it. I never did touch that wall. But there is 3 inches of polyiso foam on the outside of that wall. So we super insulated from the outside. And that's 2 ways you can do it. You can do it on the inside or the outside. Again, the upstairs roof, it's easiest to do it on the inside than the outside, because outside means you got to take the whole roof off and build it up and stuff. It's quite a job. On a wall, on a house, you can go inside or outside. I mean, there's 2 different ways. And of course, the clapboards in this house, it was all vinyl siding, and all the vinyl siding was so old it was starting to crack. And underneath it were like, 200-year-old clapboards that were all split, coming apart. So it was like, okay, this is a no-brainer. I'll put the insulation on the outside. But down here, like this walls here, these are all high-density fiberglass walls, period. These are about 6 inches deep, so we have about a 6-inch wall here. I added, again, I added furring strips. On these, what I did was the 2x4s, I added a high-density foam furring strip onto it. So what I did was to increase the thickness of it, and you can do this. You can either use wood or foam on a ceiling where you might want to have a little more grab. You might want to use wood, but here I just used foam strips. So I used high-density foam strips, and I added 2.5 inches, so I got a 6-inch deep wall. And the foam strips, of course, gave me that thermal break as well. A piece of wood doesn't insulate as well as a piece of insulation, obviously. So you could, if I looked at that wall with a thermal camera, I wouldn't see the studs, whereas in a normal wall, a thermal camera basically can see heat energy and makes it visible for you. So if you look at a house and you scan it with a thermal camera, you can sometimes see the studs in the wall because they're the cold areas that conduct the cold in. So that foam strip on top of that stud gave me that insulation so that it made a much more uniform insulation on the wall. It was quite easy to do. You just zip them off on a table saw and then just tack them up. And then when you put your sheetrock up, you use long screws. You can get 3-inch, 4-inch, 5-inch, even 6-inch screws for attaching things. So this wall is about an R22 wall, R22 to 23. Normal construction nowadays, you have to have R19 in wall structures. That's a standard. Stretch code boots that up a little bit. Super insulation, which is where I really like to get to, is minimum of R40 in a wall, R60 in a ceiling, and R20 in the walls of the basement. That's what's called super insulation. And another standard, the passive house standard, is even higher than that. That's a German passive house. It's houses that basically need no real heating systems. And those are even higher, maybe R45 to R50 in the walls, R70 to 80 in the ceilings, and the basements can be up to R40 or so. There's some real incredible advantages when you start to get houses super insulated. This house I would call partially super insulated and partially well insulated. So this house performs very, very well. I mean, I have no complaints on how this house heats, and we'll go off to the heating system later. As you notice, there's no more wood stove here.
Right.
That's a hint.
Definitely.
So as I got the house better and better, of course, it got more and more easy to heat. The changes in the house, the changes in the structure of the house, we did add a whole bedroom out here, which you'll see from the outside. Above this, we added a whole new bedroom out this way, which gave me a nice south-facing roof for some of the solar I wanted to put on. This Florida room originally had a little peaked roof east-west like this. And when I decided to do the exterior insulation on that building there, on that portion of the structure, I also changed the entire roof to face south. So it's a fairly low pitch, but it still works extremely well for the solar, so there's more photovoltaic generation up there, as well as much more insulation added in there. So that actual little room over there is completely a super insulated little room, and it does have a lot of glass in it, which of course brings down the insulation value of any structure. The more glass you have, and this is a huge hole in the wall. If you got R40 here, this is R3. So you can see how much area is R3. The whole wall maybe drops down to maybe R20. So, you really have to pay attention to how much windows you have and how you treat the windows. Again, here we deal with windows at night with a quilt. And that, of course, gives me another R4 or so and makes it nice and warm. So that's one way of dealing with windows. The other one, of course, is using window inserts, which we have the workshop for. I have some of those in the house as well. So we did add that on, and we added this on up here. I took a few doors out. There was a door in the Florida room. I took that out. There was a door in the back corner room, which we turned into a bedroom. I took that door out. That was access to a barn that used to be over there. That was sort of like connected to the barn. So we got rid of that door there and just infilled it. And whenever I replace doors, if you take out a door or a window or something, you'll look at the framing. I mean, the old-fashioned framing was, 2 2x4s are good, 8 2x4s are even better. So a lot of walls were basically tons of wood, and it was really, really excessive wood. Most houses have probably 30 to 40% more wood in them than they need to actually be good and strong. But again, it was simple building techniques. You have jack studs and everything. You have two studs on either side of a window. Then you have cross studs and jack studs coming up to support that. They go up further to support a header that go up from there. And if you take the window out and replace it with a wall, you can just basically take out all of that, just put one stud in the middle. And now you've got much better insulation value on the wall. So that was one thing I did too. When I removed doors and stuff, I took out a whole bunch of 2x4s and just replaced them with one or two. It takes a little more time, yeah.
So what would the R be of the wood?
Well, the wood is about R1 per inch. So
Yeah,
3.5
not
inch
too
studs
good.
about R3.5. Yeah, it's not too good. As a matter of fact, a lot of times you'll see, I remember over in Maine, I had a little cabin. The initial house I built was just a little tiny 12 by 24. And I could see that the ceiling, there was one space that I slept in, and the other space was like just storage. And the wood stove was down here. And of course, every once in a while, the wood stove would puff out some smoke. And all the nails in the sheetrock, which were into the studs up top, they were into the rafters, were basically even colder than the stud because it's metal. Metal goes up into the wood, and that really conducts cold. And so all these little nail heads were in the ceiling from the smoke condensing on them. So you can see even colder spots in the ceiling. And if you were to take a good thermal camera, you'd see these really cold little spots wherever the nails were. So when you drive a nail into a 2x4 stud, it almost goes to the outside, and it really conducts heat. A piece of metal is unbelievably cold. That's why the older houses, really older houses that had metal framed basement windows and some had metal framed windows. Boy, the framing was always totally frost covered in the winter, completely frost covered, because that was just outdoors basically. So it's interesting. The wood it's an insulator, but not really good. Now, if you take that wood and grind it all up into a nice fine powder, like your insulation for blown-in cellulose, that's about our 3.7. So you get the air into it. Again, all insulation is trapped air. So if you can get air trapped so it doesn't move around, then you've got insulation. And the smaller the pocket of air, the better it is. If you have a big pocket of air, the air can actually convect around. So the cold portion at the bottom and the warm portion at the top will just start to circulate. So you need to have very small spaces. Anything more than an inch, like a gap in a window, up to about an inch. And beyond that, then you start to get convective loops and it loses its insulation value. But an inch of air will give you about an R1. And what gives you insulation on glass? I mean, you say, well, glass isn't an insulator. Glass is always cold. What gives you insulation on glass is the air that comes up to that surface isn't moving once it touches the surface. So if you think about it, the air molecules that are up against that pane of glass or the wood wall or whatever, any surface, the air that gets up in contact with it doesn't move. And on the inside of the house, that air layer that doesn't move gets fairly thick. And so it sits there and gives you insulation because it isn't moving. So it isn't going to take the heat away. It'll just sort of sit there. And on the inside surface of a pane of glass, it's about 0.68 or almost 7/10 of an R value from the air film on the inside. And the outside air film, which again you can think the air is moving around outside, so the air outside is actually getting scrubbed off a little bit, goes down to about 0.17. So a single pane of glass has an R value of maybe 0.8 or 0.9, just because there's air on it that doesn't move. And that's what gives you insulation value of a pane of glass, because the glass itself has no insulation value at all. It's the air films that get stuck to it. So if you can trap air, you can get really good insulation. And so your best air-based insulations get up to about R5 per inch, maybe 4.5 to 5 at the best. Your EPS foams, that's expanded polystyrene, styrofoam, whiteboard. Your styrofoam cups, that's EPS foam, and that stands for expanded polystyrene. That foam typically is expanded with primarily air in it, and that's about R4 per inch. And you can get it in all kinds of densities. It can be really squishy foam or really good hard construction type foam, and it's all about R4. that foam that you see, the blue board or the pink board or even the green board, that's called XPS. That's extruded polystyrene. Different process. Gives you a very uniform, very nice rigid board. It does have a different chemical use to expand it, so it gets a little higher R value. Not the most environmentally friendly foam, but if you don't use much of it, again, it's going to save you more energy and save you burning other fossil fuels and other things that make nasty things in the air. So the expanded extruded polystyrene is typically used, doesn't absorb water at all. It's very good to use under foundations, wherever you're going to have soil contact. It's a very good foam for that use. Then you have your polyiso foams, polyisocyanurate, foil face foam typically. You'll see it at like at Home Depot, you'll see the big sheets with foil on it. It's all shiny on both sides. That foam gets up to around R6 to maybe even R7 because they use a different chemical to blow it that's even better. The air, again, can conduct heat a little bit. The chemicals they use to blow these foams don't conduct heat as well, so it gets even better than air foam. So you get that R7 per inch or so, maybe 6.5. So, 1 inch of foam can give you quite a bit of good insulation value, and it's totally unbroken. So, rigid foam boards, rigid board insulation is really good to use to give you that good insulating value.
Peter?
Yeah.
Aren't the pinks and the blues, I'm not sure about the green, aren't they a 10, R10?
No, it's R5
For 2
per
inch.
inch. For 2
Oh,
inch,
for
it's
2
R10,
inch.
yes. 2
Okay,
inch is R10.
that's what we've been working
Yeah,
with.
yeah, 2 inch. Typically people use 2 inch for like foundations and things like
Right.
that. Yeah, it works very well for that. They do have actually other foams with nanotechnology now. We have actually been able to create foams that it's called aerogel. And aerogel is a foam that is basically where you have air bubbles that are smaller than a wavelength of light. Incredibly tiny little air pockets. And when they get down to that size, you lose all the normal physics of how heat moves. And this insulation can give you R10 per inch. So 1 inch of it can give you R10, which is astounding. It's very expensive stuff. But if you're trying to insulate a small space, you've just got a small space, like one of the worst places in a house, and who had ice dams this year? This was a great year for ice dams because we had a lot of snow on the roofs, and snow is insulation. Believe it or not, snow is a pretty good insulator, especially if it's fairly dry snow. So the heat from your house leaking up at that critical point where your wall meets the roof, and that's where your roof rafter comes down, and most people, here's your roof rafter, and they basically cut a big notch in it and stick your wall up into there. Well, you don't have much of a space there for insulation. And typically they'll put air chutes to keep the roof cold because if you get the roof warm, it melts snow, so you have even less insulation. So that's a real critical point. And so that's where your ice dams occur because that heat, when you get a lot of snow on that roof, the heat gets trapped. And then it melts on the underside, then it gets to the edge and freezes, and then it just continues to freeze back further and further up the roof until finally the water can't get out over it, and it goes under it into your shingles and into the house. So what a lot of people have done is in a case like that, you want to put a real high insulation value material in there, and some people have used aerogel just for that one small portion. I typically have people blow in 2-part spray foam. You can get foam, again, you can get rigid board foam, or you can get foams that are basically spray foam. The old can of single-part foam you buy down at the hardware store or Home Depot, that's a spray foam, and that's a 1-part spray foam. And you could also get 2-part spray foams, which I used in this house, and I'll show you downstairs. 2-part spray foams are 2 chemicals. They mix together in the nozzle, and when they come out, they'll come out as a liquid and expand 30 times their volume or 100 times their volume and stick to anything that they come in contact with. But those types of materials have a good high R value, R6 or so, for the high density units. So sometimes I'll have people spray that into that narrow space above their wall. They might only have like 6 inches, but if you can get 6 inches of foam sprayed in there, and you can do it also with, you can take rigid board and cut it and fit it in there and then spray foam around it too. You can do it by hand. But if you can get a good high R value, you need about if you get R40 in that space above that wall and where your roof rafters come down, you'll never have an ice dam in this climate here. So R40 is like the key number. If you can get close to R40, you're going to be okay. Most people have about maybe R10 or maybe R8 or 6 out at that area. So it's just a horrendous heat loss area. And again, when we use our thermal cameras, we can see those spaces really well. So the insulations that I've used in this house, again, we've still got rock wool in it. We've got fiberglass. We've got EPS foam and XPS foam. We also have some polyiso foam, and we have 2-part spray foam and single-part spray foam. So basically, it's pretty much everything. Yes.
So what kind of foam did you put over the cellulose in your walls?
Okay, so upstairs here, we used XPS, blue board. I would have used polyiso, but back then I wasn't that familiar with foams, 10 years ago or so. I wasn't really that familiar with foams. I'd used primarily fiberglass up to that point and some cellulose. So those are my real areas of insulation expertise. But the I would have used polyiso now, and I did on later parts of the house here. The addition, the 19, let's see, this was added in 78. That end over there was added in about 49 or so. And that gave them the bathroom and the connector to the barn. That I gutted that out completely, got all the insulation out of it and everything. And I put in, carefully fit in new fiberglass, high density fiberglass, and then put an inch of foam on the inside. So those walls over there are insulated with fiberglass and an inch of foam on the inside. Again, that was because the outside was in good shape, so there was no need to take all the outside off and try and put the insulation on the outside. Again, if you're tearing up the inside of a house, hey, no problem, and that's what I was doing. I gutted this whole house out basically inside, which also gave me the ability to change all the wiring, upgrade all the wiring, which was a lot of mishmash of stuff, upgrade all the plumbing. There was basically no plumbing, and so that is one advantage of taking off the inside of an old house. You can address all those other issues. Plus also you may find huge infestations of bugs and things like that by taking off the interior and seeing what's in that wall. And I did find an awful lot of that in this house. Again, any house that has a wet basement is going to have problems in the walls. It's going to be insects, it's going to be mold, it's going to be all sorts of problems like that. Any house you walk into and you can smell the basement, there's problems in that house, and you're going to have to address them to make it a healthy house to be in. So that addition over there, we did pretty much right away. When I got the house moved onto here, when I did this out here, like 2 years after we moved it, we put this room up here. I insulated that room fully with the 2-part spray foam. So we actually used 2-part spray foam in each bay, completely, which gave me total air sealing and really high R value. So that was done with 2-part spray foam. At the same time, I had them go down to the basement and spray all the way around the rim joist, completely around the rim joist downstairs there, and put about 4 inches of foam in that space. And if you think about it, that rim joist space is above grade. It's seeing outdoor temperatures. So that's a part that if you wanted your basement to be warm, you've got to make sure that's very, very well insulated, like your upstairs walls, where it's going to lose a lot of heat. Again, basements and houses, another 30% of your heat load. Even though you don't heat it. People say, I don't heat my basement. Baloney. You're dumping all kinds of heat from the house down there. And the heater, if you got your boiler down there, it's pumping heat out through those walls. And those walls in a typical house have absolutely no insulation value. I mean, you're looking at, R1 for a typical concrete block wall or foundation wall. So that's pretty much nothing. The heat just goes right on through it. And it's very, very easy to correct that problem and correct the air sealing at the same time by using this 2-part spray foam up in that rim joist. So that's, yeah.
What about people who think that they're saving energy by insulating the wall between the basement and the house?
Well, it depends what you want to do in the basement. There are houses where I've basically made the house thermal envelope the ceiling, the walls, and the floor, and completely excluded the basement from the house. And that's another way you can do it. In that case, what you probably won't, what I typically recommend is that you insulate the walls to the basement, you insulate the walls and leave the floor uninsulated in the basement. And that way you've got, again, ground warmth in quotes. Ground is 45 degrees. That's pretty warm in the winter when it's minus 20 or minus 10 outside. So you can get a lot of heat out of your basement into that basement space to keep it from freezing. If you've isolated the house and the basement, and the only time I recommend people to isolate those two spaces if they don't plan to do anything in the basement. Maybe they have a water tank down there, a pressure tank from the well or something, but they don't have the washer dryer down there, they don't have the boiler down there. It's just a space under the house. Typically it's probably a crawl space usually. So in that case, yeah, leave the floor completely uninsulated, but put a really tight vapor barrier on it. And a vapor barrier is basically a plastic, maybe 6 mil plastic, 2 layers or something. A vapor barrier is to keep moisture from coming out of the ground. And even if you're in a basement where the ground looks like it's pretty dry, and the topsoil can be, you can lift it up and it's just fluffy. What's happening is moisture is coming out of the ground, coming up, and then it just diffuses out of the ground into the airspace, and then goes right up on into the house. And so you want to make sure that floor gets completely covered with a really good vapor barrier to keep that moisture out, because that'll continuously go up into your wall spaces and into the house itself. And then the walls themselves, we put foam on, maybe 2 inches of foam or spray foam or something. And so that basically traps the heat coming out of the ground in that space, and it'll never get below maybe 40 degrees, maybe a little lower than 40, even if it's completely isolated from the house, because the ground warmth is going to keep it warm. And so that's a really good way to deal with the basement, isolate it completely. And again, the floor wants to be totally air sealed, so every little nook and cranny that comes through the floor wants to be sealed up. Probably the best way to do that is before you put the insulation in the floor, go down there and have the person who's going to spray your rim joist to air seal that up nice and tight, have them spray the floor as well. Again, we call it a flash coat. They put like 1 inch on. They just spray it with 1 inch of foam real quick, and that basically air seals everything up. And you can also do it with a can of spray foam. You can go under there and spray all the little cracks and crannies that you can find. But you want to make sure that you totally isolate the house from the basement. Foam's a really good material to do that with. The insulation of the basement, by the way, people love to put fiberglass in floors, and that does work okay if you've controlled the moisture. If you ever go into a basement where, a crawl space or basement, where they haven't really controlled the moisture, all the insulation is dropped out, falling down on the floor, all of the paper that was on it's all rotted off and everything. And it's because the fiberglass is a place where moisture can condense. So if it gets really cold down in that space, because there's all kinds of air leaks, the moisture that's in there will condense on the fiberglass, and then it literally makes it wet. And then the wet fiberglass is heavy and it starts to sag out, and then pretty soon it's all falling on the floor. So if you've controlled the vapor and you've got that space nice and dry, then you can use fiberglass as long as you make sure you really hold it up in there well, fit it carefully, get it in there, and make sure it's well supported. A lot of times the best way to do it is put strapping every 16 inches, just wooden strapping to hold it up in there. Or you can do it with blown-in cellulose. You can stretch when you blow cellulose, you put up a fabric. It's a polyester fabric that lets air through. It's called Insulweb, is one of the brand names. You staple it up and you blow the cellulose in. You can use that underneath the floor too. You put the Insulweb up and then blow your dense packed cellulose in there. And that's a very good way to do it as well. But the isolation of the two spaces, no problem. You just have to make sure that you're not trying to use that space down there for anything that's going to require you being down there and being comfortable. Does save you a lot of energy, no question. You're not heating another space. So the rest of the history of the house here, pretty much I got a heat pump. Of course, I put the photovoltaics on right away, and the solar hot water system out here, which we'll look at in a little bit. The heat pump, of course, once I got the heat pump in, all of a sudden it was like, I'm not using this wood stove anymore. I've burned wood for 35 years. Again, burning wood is one of those things where if you want to do it reasonably environmentally soundly, you've got to burn small fires really hot. And most people look at a wood stove and they say, oh, I'll load it up with wood and then damp it way down. It's the worst thing you can do because then the stove burns very inefficiently and it's very dirty. Wood stoves are horrendously dirty from particulates and all kinds of carcinogenic emissions, especially if you burn them, cold, so to speak. So I was quite pleased to get this wood stove out. After 2 years I didn't use it. I finally just took it out and sold it. So I haven't had it now for 3 years. We've gone through some pretty cold winters here. And this heat pump isn't really appropriately sized for the house. It's a little undersized, but it still does the job well enough for me.
That's the only heat source?
Yeah. Well, I mean, I can turn on electric heaters, or I can, if I want to back it up, I can use a little electric space heater. But that's the heat source, yeah.
So it's not on an outside well?
No, this is the inside. There's 2 units. This is called a mini split heat pump.
Okay.
And the mini split heat pumps, they're mini because they're small. They're split because there's 2 units. An air conditioner is a mini split that isn't split. So an air conditioner is basically the compressor unit and then the 2 heat exchangers. The 2 heat exchangers, in this case, we've got the heating, this is in heating mode right now. So what it's doing is the outside unit is evaporating a fluid and the inside unit is condensing the fluid. When you evaporate a fluid, you have to put heat into that fluid to get it to evaporate. To go from liquid to vapor, you have to put heat in. And so the heat comes from outside. And you say, well, it's not very warm outside, but if I take air outside and I go from, say, 20 degrees to 0 degrees, I've got 20-degree temperature difference of that air. And if I take air inside and I go from 50 degrees to 70 degrees, that's the same heat. I mean, it's just, air is air. And if you cool it down 10 degrees, you can warm the same amount of air up by the same number of degrees. So the heat pump is called a heat pump because all it's doing is pumping heat. It isn't making heat. A resistance heater you plug into the wall and turn on, that's called a resistance heater that's making energy, making heat energy. So it's actually taking electrical energy, converting it into heat energy, and it does it, basically 1 unit of electricity. We buy electricity in what's called a kilowatt hour. You look at your electric bill, you see you use 300 kilowatt hours this month, and each kilowatt hour costs you 20 cents. So that's the unit of energy that we buy from the utility, and 1 kilowatt hour of electricity will make 3,412 BTUs of heat energy. And to give you an idea, 1 gallon of oil, in a typical house, you burn it in your oil burner, you might get 100,000 BTU out of it. So 1 gallon of oil will give you about 100,000 BTU of heat in the house, maybe a little more than that. And 1 kilowatt hour of electricity gives me 3,412 in a resistance heater. Now, the heat pump is the reason everybody uses heat pumps now is because the heat pump can take that same kilowatt hour of electricity and turn it into about, on a day like today, I'm getting 10,000 BTU instead of 3,400. So I'm actually getting 3 times as much heat energy with that same electricity as I would from a resistance heater using the heat pump. It's an amazing technology, and it just works by basically moving heat. And you just have to remember, your refrigerator, that's a heat pump too. The heat pump, in this case, is taking heat out of the inside, and that heat makes the fluid vaporize, and then the fluid goes through the compressor, comes out into the unit that's underneath it. That's why you feel that warm air blowing out the bottom. That's all that heat being rejected into that other heat exchanger. Down below, you'll see that heat exchanger, the one you're supposed to vacuum every 6 months. Keep it nice and clean. That is basically taking the heat out of the refrigerator and blowing it out across the floor. Inside, there's also coils. The coils inside are typically hidden inside the walls and stuff, so you don't see them. But there's 2 sets of coils in there, set of coils there, set of coils there, and 2 big fans. So over there's a fan blowing that blows the air from the house through the unit, and across the heat exchanger, and this one out here takes air from outside, blows it through the coils, and it comes out colder. And if you're out there, you can feel the cold air coming out of that unit. It's really chilly. It does quite a job of cooling it down. This unit, anybody who's seen these, again, these are primarily, they were always sold as air conditioners, and they're still being sold as heat pumps, but they can do air conditioning. If I click a button, that'll turn into an air conditioner, and the roles get changed. This puts out cold air, and that puts out warm air. So basically what happens is you can make this an air conditioner or a heater just by clicking a button. The trouble is they're sold as heat pumps, and the instructions say right at the top, air conditioner, and mount this 4 inches from the ceiling. And so everybody, you go to most houses, you'll see that unit sitting way up in the ceiling up there. And it's like, well, why is it up there? Because the instructions say it's an air conditioner and you mount it up on the ceiling. Well, how much do I use this as an air conditioner? 1 hour a year? How much do I use it as a heater? 180 days a year? So, where do you want to put a heater? You want the heater down low to the ground. You want to take the cool air off the floor, blow it through it, and warm it up. So you've got that nice warm breeze blowing out across the floor. You don't want this thing way up in the ceiling, heating up the ceiling. And so I have this ongoing battle with people and telling them, look, the heat pumps really want to be, if you want to use it for heating, mount it low. And some of the manufacturers are now coming out with specific wall mount units that are designed to be down on the floor because they're finally beginning to say, well, okay, yeah, it's a heater, so install it as a heater, not as an air conditioner. So that's why that's mounted down there low. And it's, yeah.
So is that the only interior unit in the house?
Yeah, that's the only one I have here. Some houses you can have a single compressor unit outside and up to 8 heads inside. So you can actually have one unit outside and up to 8 of these little heads around the house. If you wanted to heat a house more uniformly, you could do that. Again, the more insulated you have a house, the more super insulated a house becomes, the less temperature difference there is anywhere in the house, even with a source of heat in one point. Oh wait, yeah.
So the compressor's outside, is it outside for a reason? In other words, are there toxic fumes or anything that are coming out of it?
No, the reason that it's outside is because it has a very high flow rate of air, like 1,000 cubic feet per minute. So there's a lot of air going through it, and it's extracting quite a bit of heat out of that air. In order to replenish it, you need to have the outside air source available to it. Now there is a fellow in Maine who I've talked to. He's building net zero or less than zero energy homes. A net zero energy home is basically a home that, because it has like photovoltaic systems or something, produces as much energy as it uses during a year. So net over a year, it's zero energy. This house is actually a positive energy house, so it actually produces more energy than it uses. So this is what's called a positive energy home. And this fellow's designing homes that are super insulated, and he had an idea. He wanted me to see if I could run some numbers for him to see if it would work. His concept was, you have a house, you super insulate it, really thick walls, really thick insulation in the ceiling, really good insulation in the foundation, all the way underneath and everything. But in this case, he's not going to put the insulation in the floor, underneath the floor of the basement. He's going to leave that open. And then what he was going to do is put a dividing wall in the crawl. And again, he has a 4-foot crawl space under the house that's fully insulated. So the envelope is basically the house up here. The basement is separated completely. As we were talking, how do you separate the two? So this has got really good separation. In the basement, he's putting a dividing wall down the middle. He's leaving an opening here and an opening down here. So then he's taking his compressor, his outdoor unit, and he's putting it in the basement. And now he's basically running this unit that's going to take heat out of the air in the basement, and it'll take the heat out of the basement really quickly. But if he's only using a little bit of heat, and the house is so well insulated, it only needs, like in a really, really cold weather, it only needs like 6,600 BTU, which is a very small amount of energy. So he basically has enough heat recovery from the basement floor, again, that ground warmth. If he cools the basement down to 35 degrees with the heat pump, the floor will give up enough energy to replace that heat. And so he's got the heat pump in the basement, running at 35 degrees, which is fantastic. They run unbelievably efficient at that point. The colder it gets outside, the less heat energy the heat pump can put out. It takes more and more work to get that heat out at that colder temperature with the fluids they use. So in this case here, you've got the heat pump in the basement. It's taking heat out of the basement, putting it into the house, running really, really efficient. Doesn't have any problems with clogging up with snow in a snowstorm. Doesn't have any problems with getting all frosted up because of the moisture in the air, because he's taking all the moisture out of the air. And so it's an incredibly clever system. And to add to it, because the house is super, super tight, he has to put a ventilation system in. So his ventilation system is to put little inlets in the various rooms, has a fan in the floor of the house that blows air into the basement. So what he does, he draws air in, that air gets heated up in the house. So that's, that takes some energy. But the air he blows into the basement, the heat energy, that gets taken up by the heat pump and put back into the house. And then that pressurizes the basement because he's blowing air into the basement. So when you blow air into a space, of course, it gets like blown into a balloon, it gets pressurized. So radon can't come into the basement because it's held out. And then he's got a stack over the corner that goes all the way up to the up to the roof and vents out. So he's getting all these little benefits from this design, which is only possible because it's a super duper insulated house. But it's not something you can't do to any house. So it's really kind of a clever solution to heating in New England, unbelievably efficiently. I mean, this house is going to be incredibly efficient. I mean, this house isn't super duper insulated, but with that heat pump, I think this year I think I've used about maybe 1,500 kilowatt hours of electricity to heat the house, which is not a lot of electricity, and that's not a lot of energy. Again, I don't keep the house at 70, and in the morning I'll come down, it'll be 60 or 58 even, because I set it way back. But it's done quite well this whole year, and this was a pretty cold winter.
So would it make sense to put the compressor in a shed?
No, you want it, if you haven't got a special situation like this,
Okay.
you want it outdoors, because you want it to get, but you do want to cover it, that's one thing. You want it to be, the ideal place to put it is like underneath a porch, where you've got full access to air, but you haven't got any snow getting on it. Because one of the big problems is if this was heavy as snow here, the heat pump's running, it's a giant vacuum cleaner, it's sucking all that air into it, and that just plugs it right up. And then in order for it to operate, it's got to stop, melt all that off by actually reversing its cycle. It turns into an air conditioner, but it doesn't run the fan inside. It gets the outside unit nice and toasty, and when it gets up to 70 degrees out there, it shuts off, which means it's melted everything off of it. Then it starts up again. So every time you do that, of course, you don't have heat in the house for 10 or 15 minutes while it's doing all this. So we tend to put them where we can get a cover over them, and then they run really well. They don't have this problem of turning into a defroster all the time. Yeah.
What's the temperature difference between this part of the house and on the other side of the wall or upstairs?
Upstairs, it's a little bit cooler upstairs, and it's definitely cooler than when we used to have a wood stove. Because when we had the wood stove, you couldn't stop all the heat from going up the chimney, up the stairs. So the upstairs, with this heat pump here, the upstairs probably runs 5 degrees cooler than down here. In the dead of winter, our bedroom here, which actually steps down, so it's kind of a cold trap, might be in the high 50s in the dead of winter. But again, when the sun comes up, it warms up immediately. The back room, if I have no heat on in there, it just gets plain. If I shut the door, that'll just get down to like 45 or 50, because there's no heat source back there except from the basement and through the wall, of course. But there's no way to get heat in there. I do have there's also a gas propane heating system in the house, baseboard hot water system that I put in when I first built the house, because the insurance company wanted a real heating system, not a wood stove. So I put in a boiler system. It's a condensing gas boiler, so it's a very efficient boiler, direct vent, doesn't need a chimney, it just vents out the sidewall. But I haven't used that in 8 or 9 years. Matter of fact, this loop right here, these baseboard units you see here, these are actually connected up as a dump loop for the solar hot water system. So when the solar hot water system gets the hot water tank all heated up, it just dumps heat through here and keeps the house roasty toasty and the heat pump doesn't even run, so if it's a sunny day, it's an added benefit, yeah.
We had a really cold winter, and that doesn't really work under 10 degrees or under 0 or something, so what
Well,
were you
actually,
supplementing it?
that's an older unit, it's rated at plus 5 degrees Fahrenheit. The newer units are rated, the newer high efficiency units are rated at minus 5.
Okay.
And they actually operate down, I mean, this thing was operating at minus 14 a couple of weeks ago, still putting out heat. I mean, they just don't get very efficient. But they're still more efficient than electric heating. But the thing is that the amount of heat that they put out drops off. So your house is getting, minus 14, the house requires a lot more heat energy to keep it warm because it's got more heat loss. This unit is putting out less and less heat because it's so cold outside, and so the house just starts to cool down. So at that point, if I wanted to, I mean, it didn't bother me, I just put a sweater on. But if you wanted to, you just flip on a resistant heater for that period of time. So you're using, a little bit of resistance heat to warm the house. I mean, one little plug-in, wall heater puts out more heat than that does when it's that cold by quite a bit. So that's one very simple way to tide yourself out. Or you could have if I had a pellet stove here, you kick the pellet stove on. But like 95% of the time, that's doing all the heat load and keeping the house toasty. So again, it's only those really bitter cold periods. But the newer heat pumps, they'll go down to minus 20, minus 25 and still put out good heat. The new model of that, Fujitsu for instance, like I said, this is 5 years old now. So it's fairly older technology. And yeah.
But in your case, you also have solar hot water that goes through a heating system?
Yeah, the excess heat. So if it's a bright sunny day outside, the hot water tank, of course, heats up really quickly with that system out there. Then there's a little valve downstairs that just changes over and starts to pump the hot water through the baseboard here. Usually what I do is I have it just go through a dump loop in the basement. But I said, hey, I've already got these up here, so why don't I connect these up? Because I don't use my gas heater anyways. So I just got some valves down there I just throw and it goes through this loop. Otherwise it goes through the gas boiler.
So it's manual.
Well, no, it's automatic, but there's manual. If I threw the manual valves, I would cut this loop out of the solar system. It would be connected to the boiler. The boiler would then be supplying it. So I just cut it out. But it was just something that I said, hey, I got to put it. Again, this is a really big hot water system, and it's way oversized for the hot water tank. So in the summertime, you have to have some sort of way to control the heat with this specific type of system. So this system needs some sort of a dump loop or some sort of control circuitry to make sure it doesn't overheat. What I do is in the summertime I just cover up the collectors because the ground mount's really easy. Just put a tarp over it and get to whatever size you want. That's 4 main collectors. We could actually use one of those collectors for our hot water needs. But with 3 of them, it'll even do it in the dead of winter. In the dead of winter, it'll put out enough hot water. Again, with solar, if you can manage your loads, your solar can be 100%. My hot water, they say, solar hot water can give you 75% of your hot water. Well, if you wait for a sunny winter's day to do the wash or take a shower, you've got 100% solar. And it's very easy to do that. But again, it requires manipulating your demand, manipulating your loads. And same thing with solar electric. You could actually run a house without a connection to the utility, without having a storage system, if you ran your loads during the daytime when the sun was out and let them coast overnight. And that refrigerator is an energy storage device. I can let that'll actually coast for probably maybe a day or two without running before things start to have problems. So that's stored energy. It's stored cold. Your hot water heater in the basement, that's storing energy too. It just isn't electrical energy, but you can use electrical energy to make it hot, and then that's storing energy for you. So this house actually has an inverter system in it. There's an outlet. You see that outlet right there on the wall, the one on the left. That's a power system. That's a dead outlet right now, but if the power fails, I flip that switch on, I can run directly off my solar arrays. I have no batteries right now. You just run directly off the solar arrays as the sun's out. So there's daytime power, and it's just a matter of flipping a switch when the sun's out if the utility fails.
Can you say that again, Peter? How do you get it to work?
Well, what happens is the inverter downstairs, which is the device that goes between your solar panels and your circuit breaker box. It's a device that actually makes the power from the solar panels into what the utility supplies you. It also has a circuitry in it to make electricity directly from the solar panels. It has the proper timing devices to make 60 cycles, and it has the proper devices to make the voltage just right and generate that nice power curve that you get from the utility. It has it all built into it. They just never used it with the proper outlet to give it to you. So this one company said, well, why don't we just simply set up what we call a secure power system, and when the utility power goes out, rather than the inverter sitting there dead doing nothing for you, you can turn it on, and this outlet will give you 1,500 watts of 60 cycle, 120 volt electricity, just like that.
Wow.
So they just added one little device to it, and all of a sudden they've got this nice little circuit.
That's
So
great.
it's really a convenient system, and so that's just one of the advances they've made in some of these systems. Also in old houses, by the way, you have all these interesting things like this floor had a really cruddy green carpet on it, so we peeled the green carpet up, peeled up all the plywood that was underneath it, and there was this beautiful wide pine board floor under it. And upstairs, all the pine boards upstairs, which are these big wide pine boards, were covered with a brown milk paint, so we scraped all that off and sanded it, and got nice old pine floors upstairs. Same thing in the kitchen area, that was all covered with this really cruddy linoleum and plywood. We peeled all that up, and here's a northern yellow pine floor underneath it. It's still in pretty nice shape. So, those are some of the fun discoveries in old houses that you come across. Of course, wood floor is really nice. Just put a nice rug on it, nice wool rug or something, and you got a really warm, toasty floor to stand on. But let's go outside and just look from the outside and check out a few things and some of the other systems outside, and then we can come in and we can go down the basement and look at all the systems down there. We can also take a break and have some coffee, cake, and tea or something. Yeah.
I had a question about your PV. Is it a hybrid system between micro inverters and then another system for the inverter down cellar?
Well, actually, the systems I have here, I have a couple panels out by my observatory there that have microinverters on them.
Okay.
But all the other inverter systems are what is called string inverters. So you have one big inverter with a whole bunch of panels connected up to it. I'm not a real fan of the microinverters because I'm a mechanical engineer and I really know about heat, and I just don't like the idea of putting an electronic device underneath a solar panel where it's going to get cooked to about 170 degrees on a roof amongst a whole bunch of other panels. If it fails, it's a real pain to get it out of there. So that's my whole feeling on that. Plus, it just doesn't run as efficiently when it's that hot. So I like to have the string inverters. Plus, I also get the advantage of being able to have that secure power system with it as well. It's less expensive too. String inverters are less expensive, and the shading problems they're blown way out of proportion. Your panels all have the ability to bypass. If you get shaded on a solar panel, it can bypass that shaded section, and you just cut your output by a tiny bit. It doesn't really drop the output off much at all.
Is that a module you add under them nowadays to manage that power?
Well, they do have other inverter systems where you have a main central string inverter and then optimizers on each panel. That's another way to do it, but it's like, why increase the complexity, So I like to try and keep it as simple as possible, and that's why I like the string inverters. They go up real quick and easy. So why don't we get our shoes and coats on here, and then we'll go outside and take a look at some of the systems. Then we can come in and, like I say, we'll have some tea and cider or whatever. All the foundation, all the foundation stones that used to be made underneath the back addition. And so I took them all out and just made a simple walkway out of it. It was great. I had tons of them. They worked out really well. So that's the center core of the house, that portion right there. We did add a skylight up to the bathroom. That gives us some nice light up there. I do like skylights, small skylights, big skylight. Again, a skylight is, you can see the skylight has a curve that comes up the sides. Well, the curb is only a little thin piece of wood, so skylights are pretty inefficient energy-wise. I did improve that though because I have one of our little thermal inserts stuck in that unit that's down at the ceiling level, so it actually does improve that skylight's performance quite a bit from the heat aspect. So that was the addition put on that connected to a barn back in '48, and this is the addition that was put on in '78 as the sunroom. Now you can see on the outside of the foundation there's a cement board. This is that half-inch cement board they use for backer underneath floors and things like that. I've got that covering up 2 inches of foam. That's a very easy way to insulate the outside of a foundation. You can dig down on the outside, a foot down below grade, put 2 inches of foam board, and then put this insulation, this cement board against it to give you protection. And it's really durable. The cement board lasts forever. And then you can see there's a little piece of flashing. I just put a piece of flashing up under the underneath the clapboards, and you can see it just skirts out over over that to protect it. So that gives you the rain just runs off the edge. That's cement board. And it comes in 3 foot by 5 foot sections for about $10, and I just cut it in half and use it 18 inches deep. I screw the top of the cement board to the sill through the foam, so it goes through and it's hanging. Now this whole front of the house, from not the addition over there, but starting over at that inside corner, all the way across the front, all the way around here, is all done with 3-inch polyiso foam on the outside. So basically I stripped off all the clapboards, and you can see how this has been built out.
Right.
You can see the depth of the window. The windows stayed where they were inside, and I just added a 3.5-inch piece of wood to the frame. I used a really high quality sealant on that. So this frame, I made this frame up with a new sill extension, and I just screwed it right in. And then I put new trim on. And behind these boards here are strapping. So I put the foam on the wall. The foam was like right up against the original boards. And I basically was very careful to foam the joints and tape them. And then I put 1x3 strapping on the face of it, screwed right in, and that held the foam in place and held the strapping on, and then your clapboards nail right on that. So there's actually an air gap. You can see there's a gap up top, and there's a gap underneath here, so the air can actually move behind it. So the clapboards are always really nice and dry. They don't get wet and stay wet. They dry out very nicely. So this was all done with that 3-inch foam around there. This actually, I did this section with spray foam just to show one of my classes how you do spray foam as well. So this was actually done with 3 inches of spray foam, the same technique of the vertical strapping and the siding on it. Now over here, by the way, up top there that's 2 kilowatts of photovoltaics, 2.1 kilowatt up there, 2,100 watts. There's a little over 1,600 watts of photovoltaics on the garage. And again, see, I just used the roofs that I had. I didn't have one great big roof here. I had a whole bunch of little roofs. I had to put that over there since the maple trees didn't shade it too badly. And that works quite well. This works really well, except it does take a little bit more effort to keep this clear. I have a snow rake that I can pull the snow off with. When I was redoing this wall, putting the 3 inches of foam on here, I said, hey, why don't I put a hot air collector between the 2 windows here? And this can help warm up the basement, which is, of course, my floors. It's sort of like a floor heater. So it's like in-floor heating, so to speak. What I did here was I basically built out a curb on either side. Again, the depth from here to the wall, this is clapboards, and there's a 3/4 board, then there's the foam insulation. This is about 2 inches deep. I just built out a curb, and I have a piece of that black surface in there. It's just basically very thin aluminum flashing that is 1 inch off of the foam face. The foam face I just left as foam. I sealed it all up with tape and everything. And then I built out some little curbs that hold it off. The air is coming in. We'll see it down below in the basement. There's actually a hole in the sill down here and another hole in the sill over here. And the air actually comes up behind that black piece of aluminum. It's not underneath this surface, it's underneath the black surface there. The air comes up, goes around through a channel pathways and back down and into the basement. So it gets drawn in here and blows out there. You can hear it running right now. So there's actually enough heat in this right now to warm up the air, warm in the basement. And then this is called Calwall. This is made over in Manchester. It's just a fiberglass material. It's translucent. It's a very, very efficient light transmitter. Very simple to use, and I just simply screwed it on, used some aluminum flashing on the sides to make the unit sealed up. And it works like it can be. This is a 35-year-old solar panel. You can see a little worse for wear, but it still puts out about 90% of its power rating.
Wow.
And so, unbelievably durable. And that just simply connects up to the little fan down there, directly runs the fan. So there's no need for any utility power to make this operate. It just runs by its own little solar panel. So
Cool.
it just starts up and turns off.
What size is that, Peter?
What's that?
What size is it? The panel?
Size? It's about a little over 5 feet wide, about 7 feet high, so about 35 square feet.
Wow.
Yeah, so it does a very nice job. On a typical winter's day, that thing will be blowing 120, 130 degree air into the basement.
Wow.
Taking
Fantastic.
about 58 or 60 degree air from the basement. But it does a nice job. It just keeps the temperature up a little bit, and that helps your floor stay warmer. So these big pipes here that come out, these are this is just regular old black, unperforated black drainage pipe, and inside that there is a copper pipe wrapped in insulation, and that comes over to our hot water system here. These are standard flat plate collectors. Flat plate collectors are basic collectors that just have a glass panel. They have a copper plate inside the tubes. There's a header that goes across the top and another header at the bottom, and the vertical tubes connect the top to the bottom. Fluid goes into the bottom, goes up through the tubes, comes out the top, and there's 3 here connected in parallel. So basically, fluid comes in over here, goes all the way across, the headers connected at the bottom, and then goes up the riser tubes, comes up to the top, and then comes out. And so you see the piping going across the ground and then underneath the ground. And so I buried the piping underneath the ground over into the house, and I also put some insulation. It's only like a couple feet under the ground. I put some more foam insulation on top of that, some XPS foam, to make sure that it was a little better insulated. Again, makes it lose less heat to the ground. Again, 2 little old solar panels that I had kicking around to run the pump system for this. So when the sun comes out, the collectors warm up. When they get warm enough, warmer than the hot water tank in the basement, the little controller down there turns on the solar power to the pump, and away it goes. So this can operate without any utility power. It just runs by itself with its own solar panels.
Peter, do you clear snow?
Yep. Whenever there's snow out here, I'll clear it off. Like as soon as I'll clear off those panels up there. Again, they'll melt off really quick. It's a little bit like this. If the sun came out bright here, these would all melt off within literally a half hour. But when you get a real heavy snowstorm, I'll come out and clear these off. Again, the winter time, you want the heat. So the only way you gotta get that snow off.
So you use a roof rake? Is that what you said?
I have a roof rake for all these. I have a roof rake that has it's a metal roof rake, but I put some foam and Tyvek tape on the lip of it, so it's got this nice soft surface. I just pull the snow right off, and it's really nice and easy. It doesn't hurt the panels at all. And again, I've been clearing these for years, and there's no damage at all.
How do you get up there?
I just put my step ladder, and I just have a long. Well, that's the snow rake right there. I just keep it on the clothes rack.
Oh.
So I just put up a step ladder, and I just climb up the step ladder and just rake it.
Perfect.
And usually you only have to rake the bottom of it a little bit, and then the rest will come off. Again, it's dark blue, so they really absorb the light and heat up quite well. So that comes off. You see the chimney there coming out. I just have the cap on the chimney.
I like your barrel.
The barrel of it. The chimney, it's funny, now the chimney does poke up. The reason I took the chimney off is because it does shade the left end of the solar array up there. It will shade it a little bit. And that's where I first realized there wasn't a lot of impact in the shading, because that shade of that chimney would go right across the array, and it maybe cut the array from putting out 1,400 watts down to maybe 1,150. So it wasn't a big drop in power out, but it was like late in the day I'd see that happen. I'd say, yeah, I'll take the chimney off. So this end of the house up here also has 2 inches of foam underneath. I actually put 2 inches of foam
vented space up there as well in that gable end, when I was redoing that whole space up there. And we spray foamed in the top triangle section of this new roof. We spray foamed the wall. Again, we flash foamed the floor to air seal it all. And the 1 inch, then we sprayed 2 inches up against the wall face as well. And that joined into the 2 inches of rigid board I put on the outside up there.
Peter, what's that box up there on the right, below the panel?
That's a junction box. It's a transition box. The wires coming out of the solar array go into there, and they connect up to wires that come down through the conduit on the side of the building. These conduits bring down the solar electricity. Go into the big heat pump, and I just have a little cover over it to keep the snow from just dumping on top of it. I have more elaborate covers on other ones. This is I had a piece of metal around it. It seems to fit pretty good. But if you feel the air coming out of here, you can feel it. It's chilly. It's cold air, but it's cooling it down, so it's extracting all that heat out of it. I also have it in the house. I have what's called a heat recovery ventilator. It's the fresh air system, and so this vent here draws fresh air in, and then the stale air is vented out there. And I figured, hey, I'll have the stale air vent out behind the heat pump and help warm the heat pump out. So that just gives a little more efficiency.
Peter,
Yes.
did you have a lot of snow all around here? Did you have to keep the snow away from here?
No, because it's interesting. This is on the northeast side of the house. Well, the northeast wind's blowing this way. It's the east side of the house, but the northeast winds blow this way. So when we have a big snowstorm, this tends to stay quite clear. It's really interesting. I don't recommend, when a heat pump's set up, you definitely don't want to put it on a wall where you get tons of snow buildup. Like you don't want it, I wouldn't want to put it over there. If I put it against this wall right here, all the snow would fall off on top of it. So you want to put it on a gable end like this, and you have much less problem. I don't like to see them on the north side of the house because they really do get cold. They really run much colder out there. This gets early morning, sun comes in here, and so this becomes like a microclimate, and this whole area warms up a little bit more than the north side of the house for sure. And of course, this benefits from it, so it's much more efficient operating. And they just hook up with 2 little copper pipes and an electrical connection, and that's it. So this one communicates with the one inside, and this controls the one inside. So they talk to each other.
So is there not a limit to how far away? That seems pretty far away.
No, the standard unit, again, this unit comes all pre-charged with the Freon. So all you do is you put the 2 units in, the interior and the exterior and the interior unit. You have a refrigerant fellow pull a vacuum on the system and evacuate the lines out to get all the moisture and stuff out of them. And then they just open a valve on this unit here and it fills it up. And it could go up to about 54 feet distance between the 2 units. So no problem there. Minimum of about 9 feet, and depending on the manufacturer, typically up to about 50 feet or so. So no problem getting a long distance between them.
So the connection for the 2 units to the inside, does it go from those along here?
The refrigerant lines are right here, and they just simply go into the wall, go underneath the floor, run diagonally over, and then come right up.
Okay.
So I like, again, when you put them into you retrofit a house, I like to come up through the floors and stuff, and you can see that inside there's a little wood enclosure, and behind that little wood enclosure are the refrigerant lines and the electric lines. Because they're easily accessible. I like to have everything fairly accessible, even if it does mean you put a little enclosure over it that's inside the house. Other people will mount them in the wall. They'll actually drill holes through the wall and have it come through the wall, but then the pipes are all bent at odd angles, and you have problems with moisture. When it's used as an air conditioner, you don't get good drainage out of it. So some installations can be simpler than others as far as maintenance goes in the future if you have to do it. Of course, I replaced all the windows in the basement. All the windows in the house, some are new. These are new, but the other ones I used are Canadian window Allsco. It's a company that makes, they just make replacement windows, but they're a Canadian firm, and so they use the coatings that they use on the windows are coatings designed for northern climates. They actually will let sunlight through and give you a good heat gain from the sun and still reduce a lot of heat loss from the house. A lot of coatings used in U.S. windows are mainly used for southern climates where they're made to reject solar gain. So you stand in front of the window and you don't feel any sun even though the sun's shining in. It's because it's rejecting all the heat. And they do that because they don't, most houses in the south don't want to use air conditioning as much, so they want to reject all the heat gain. So you have to really be careful when you get windows with low-E coatings, that the low-E coatings are actually designed for northern climates, not southern climates. And the Canadian windows, of course, are all northern climates. This is a little photovoltaic array, 2 different modules, because there were 2 different times I got these. That's one advantage of the microinverter systems is you actually can do an installation and add a panel and add another one and add another one. You can do the same with a series string inverter, but you have to you have to plan ahead exactly. In this case here, I have 2 different, totally 2 different modules, and here are the little inverters right here. These are made by Enphase. And so this little inverter just takes the power out of this and connects it up to my electrical system in the observatory here. And the other one does the same thing. So this is a very simple system. I have it set up on a little rack that I can just adjust the angle. And I do need to adjust, this is the winter angle, I do need to adjust it to get it to a shallower angle for the rest of the year. Typically, if you want to get year-round production from a photovoltaic system, or like connected to the utility, you want to be at roughly your latitude. Typically, in this area here, 37, 38 degrees will give you the most production over the whole year. And of course, with this system with net metering, you want to get year production, not just winter or summer production. If I was using this as if this is an independent home, where your winter usage is going to be the big problem because you have the least sun, you have the most electrical usage typically in the winter. I'd want this to be set at a real steep angle for most of the year. But if you have a ground mount, of course, you can adjust it for the season. But if you've got a fixed roof mount, of course, that's the way it is, and that's the way it's going to stay. So I do get out here and clean this off, and I do adjust it for the season. And if I wanted to, I could put another array out here and add a couple more and connect it up and make it bigger if I wanted.
And where does this energy get used?
This goes into the circuit breaker box in here, goes up into the garage and back into the house. And
Oh, so it's part of the home system?
this is part of the whole system.
Okay.
This is about 400 watts of generation. This puts out about every 1,000 watts of solar panel in our environment here will put out about 100 kilowatt hours of electricity a month. So this is putting out about 40 kilowatt hours a month, this little system here.
And how much does your heater take?
The heater? Well, we can see this, how much it's used this year downstairs, but typically around 1,600 kilowatt hours to heat the house. So typically I'd need about, 2,000 watt solar array would more than do it. So that's the thing, a lot of people are starting to sell systems where they're selling you solar panels and the heat pump as a unit. They'll sell you the heat pump and the panels to run it. No, it's getting pretty amazing that the cost of solar panels coming down so much. You actually have a heating system that runs itself. No cost. The cost of solar electric systems, when I first started to deal with them about 30 years ago, back in the early 80s, it was $20 a watt for solar panels. And now I can get them, anybody can go on the internet right now and buy them for 70 cents a watt. Wow. And that's in 2015 dollars, and I was talking $20 in 1982 dollars. So you can see there is some solar energy today, even on cloudy days. You do get the solar energy. It isn't heated in here. So I have the microinverters out there. I have one inverter downstairs and this inverter here. The technology inverters has changed. What these inverters have in them is the ability to look at a solar panel and adjust how the solar panel gets loaded. A solar panel, not to get too technical, but a solar panel puts out a voltage and puts out a current. The voltage is basically not fixed, but it tends to be right up. You come to your peak voltage. The minute the sun comes up, the panels will put out voltage. The current is mainly the factor based on how much sun is hitting it. So if it's really bright sun, you'll get the full power out of the solar panel. There'll be a lot of current and a certain voltage. And if it's not very sunny out like today, you'll still have that same voltage, but you'll get very little current. Current you can think of as like gallons of water coming out of a faucet. So if there's not much current, you haven't got much going on. But this device has a really interesting circuit in it that will basically look at the solar panel, and it'll adjust how much it gets loaded down to maximize the power coming out of it. And that's very critical for getting the most out of your solar array. What they've done in the new ones is they've actually got two circuits in the inverter now. Instead of just one circuit that you put your solar panels into, they have two circuits and do that same type of what's called power point tracking to maximize the output. So that means you could have a solar array on this side of the roof, you could have another solar array over on that side of the roof, totally different solar arrays, and they connect into the two different circuits in the inverter. So the new one I have down in the basement, actually I took those two different arrays, one sitting on that flat roof and one sitting way up high on the other roof, totally different, mismatched arrays, different sizes, and they both feed into one inverter in the basement. So it's kind of a new technology that they've added to inverters. This one is a single inverter, string inverter, running that one array up on the roof, and it's putting out 99 watts of power right now, which is about 7%. So even on a cloudy day with snow, we're still getting 7% generation. Not bad. It's got there's snow on the array too. So it's pretty amazing. You can actually get quite a bit of power on a crummy day. So this is just feeding into the one of the circuit breakers here. Then that feeds into the house and goes through the meter on the side of the house. The meter that's on the house is a net meter. It's got two channels in it. One is measuring the power you're using. One's measuring the power that's going back to the utility. So then the utility takes the two readings and nets them together. These meters, I have these meters. You can buy these meters for this is a rebuilt meter made by the Hialeah Meter Company, or rebuilt by Hialeah down in Florida. That's like $17. So I put these meters on all sorts of things just to see what's going on. And this array has put out 8,600 kilowatt hours in the last couple of years. So it's really cranking right along. Again, this would put out probably 1,600 kilowatt hours in a year. And so that's showing pretty good. Actually, it's been putting out probably close to 2,000. Been going for about 4 years. So that's one system as far as the house. Again, inside the buildings, we use metal conduit to run the power. And there's a lot of new warning labels and things that they want on them. These are the older labels. Now they got labels with big orange colors on them and white backgrounds, so they really stand out. And, again, it's all for safety of firefighters and responders and stuff. They're all very concerned about solar because it's kind of scary new stuff.
Yeah.
So try to make it safe for everybody. But I do have electric, again, everything I use runs on electricity. Got electric lawnmower, my electric bikes,
Yep.
electric, trimmer for the bushes, things like that. And it's just, I use the electricity. I have a little electric snow blower that works slick. I've used it in a foot and a half of snow. It's amazing what they're making for electricity now. And again, all that comes from the solar arrays. So it's all, I don't buy any gas or anything. I just use the electricity, and it all comes out of the solar. I want to get an electric car that'll have about 120 miles of reliable. That's my only problem is that there's just not enough range yet. And it'll be about maybe another year we'll have them with that range, and then I'll get an electric car. But for now, the Priuses do pretty good. My Prius truck, the gray one, the dark gray one, I've got a trailer hitch on it. And I tow 1,000 pounds in that all the time. I have a trailer. It's a great truck. One thing I always do with my garages, I always put skylights in. You know, skylights are just so nice to have. They put so much nice natural light in the building, so you can work in the building without having to have artificial light going. And they're very simple to add into these roofs. So you just buy them clear panels, they go right in. They have those concentric vents, so you just have one vent that draws air in and blows the exhaust out.
Wow.
Simple system. Well, the walls that really need support are wherever you have a roof, where you have the rafters come down onto a wall. That is a wall that really needs support. So like in this case here, my roof rafter came down in here. So what I have up in here is I have three 2x10s running across, and they're being supported on these posts and down onto posts in the basement. That's into the basement. There's posts right underneath here that go down into the floor.
Okay.
So I've picked up the load from all those rafters and the roof load onto these. So on an end like this, depending on your roof structure, the roof is basically a triangle. So the roof load is trying to spread the building like this, and that is taking the load, pulling it this way. Now there's no real load pushing down on that wall, not like on this one here. We know that the whole roof weight is on that wall, so that wall has to support it. This here, I could literally take the entire stud wall out upstairs, and that would be fine. I could take this entire wall out here, and it would be fine.
Oh, yeah?
Yeah, really.
Okay.
Because you're not really, you haven't much of a load on that. So windows on this side of the building have to have a big header above them to support the loads coming down. This over here doesn't need a header at all. That can just be two 2x4s and a wall across it. If anybody needs a bathroom, right over there.
Cool, thanks.
Yeah, so let's see, I'll make up some hot water. Anybody want tea or? It's just, I find that electric stoves just don't do it for me, and they have pretty high peak loads to the utility anyways. Induction cookers, induction electric stoves are pretty good. They're coming along. They're just so frightfully expensive. They shouldn't be, but you know, they're just not big in production. That's another option, and then maybe a gas oven. But the amount I think I used 8 gallons of gas in the last 2 years, so it's not like it's a lot of propane.
That is that little tank out there. That's your propane tank.
I used to have, when I first put the heating system in here, the propane company said, "What are you going to use the propane for?" I said, "Well, we use a gas dryer once in a very rare while, and we do have the gas for hot water and occasionally heat maybe, and we do have a gas stove." I said, "Oh, okay." So they came down and put these 2 huge tanks. You know. I was like, okay. So about 3 years later, they started to bill me for the tank rental because I wasn't using any propane. So I told them, "Why don't you take the tanks out and we'll just put in something for this." So I had that one little tank, and I still have a $250 credit with them.
Wow. So how do you dry your clothes then in the winter?
In the winter, put them on racks in here, and put them on a rack in front of the heat pump, and humidifies the house and dries them out in no time flat. Works really. I just have you have two folding wooden racks, and if it's sunny, the sunroom is nice and warm too.
Right.
So it works really well.
Yeah.
It takes no time to dry stuff in the winter, especially because the air's so the humidity's so low.
Right.
So it works very well.
Clever.
If he wants to, he can screw around.
Thinks of everything, doesn't he? Go
Yeah.
ahead. I've never heard of this solution to a wet basement before. It's just like building it above the water table.
Right, what's that? Oh, no, leave it open. So, behind me you can hear, this is a little fan. I just have it hung on I have it suspended so it doesn't vibrate the floor. But it's just simply a little centrifugal fan blowing air up in, and then the warm air comes out over there. I have a little thermometer here just for my own information. 59-degree air going in, 67 degree air coming out today. So that's warming it up a little bit, but it's just simply blowing the warm air out across, on the side of the floor. So it's just a very simple little hot air collector. Again, with old houses, you can see new construction, old construction. They actually sistered up all the old chestnut timbers that went across with a whole new floor system. And then I, of course, added appropriate reinforcing to make the floors a little less springy. They were spanning 14 feet here with 2x8s, which is a little bit excessive. But again, old houses, sometimes you need to do a few little things to strengthen things up. These two posts here are basically underneath the posts up in that wall I took out, so those just distribute the load down onto the floor. This is the Sunny Boy inverter, the one that has that secure power system connected to it, and this is showing the power output yesterday and then power output today. Not much today. 215 watts of power coming in at the moment. We put out all of 0.3 of a kilowatt hour today, so not a lot today, but something. 22,650 kilowatt hours over its lifetime of production. Here's my meter for my heat pump, 8452. So let's see. I just kept a little record here. Starting in June of 2014. That was pretty much the end of the heating season for sure. We had 6853. So we've used about we're up to about maybe 1,600 kilowatt hours total this year. So a couple of years ago, a year ago, we did about 1,700, I think. So we haven't quite used as much this year yet, but we'll use a little more in April. But pretty much the heating season is over as far as this house is concerned. So the heat pump will run just a little bit occasionally. So this system has, again, 2 channels in it. So it's got that one array that's over there, steep pitch, 9 panels connected, and then the array on this roof over here. They both feed in. There's 2 channels, so this has 2 channels built into it. You can take 2 really different arrays and connect them right up. So it's a pretty nifty little system, and it gives you all the information you need on the output. And you just hit it, it comes on, so that's just maintenance free. It just sits there and does it. So there's no need to pay any attention to any of this stuff. The hot air, the fresh air system is over here. And you see this pipe here coming out. It goes up through the floor there. That goes up behind in the corner of the room. I just brought it up through the building. Didn't bother to try and stuff it inside a wall. There's no need. I just put it in the corner and brought it up. That goes up into the bedrooms upstairs. 2 bedrooms upstairs, it splits, and then there's a vent in each bedroom. So basically, air comes in through this pipe over here, comes into the unit. I've got the unit on a timer, so it runs for 3 hours on, 3 hours off. And I'll just turn it off right now by plugging it. This is a unit made by Fantech. This thing only costs $550. It's not a really expensive unit. And the key to it is this right here. So this is the heat exchanger. And you can see over the season it does tend to pick up a little bit of debris. So I will be cleaning this out in the spring here.
Yeah.
But what this consists of is basically a whole bunch of aluminum plates this way, and a whole bunch of aluminum plates this way, and they aren't joined together, so when the air blows through here, it transfers heat to the air blowing through here. So it's a very simple little heat exchanger. About 65 to 70% efficient. The fans that are in here are extremely efficient. They're called ECM, electrically commutated motors, which is a fancy way of saying very efficient motors. And they draw about 40 watts of power, which is not a lot of energy. So you're not using a lot of energy to operate this thing. I think I use about 15 kilowatt hours a month during the typical day, typical month of operation, 3 hours on, 3 hours off. But this does a great job of keeping the air in the house really fresh. And again, this house is, most houses, half an air to half to one full house air change per hour is a typical leakage of a normal house. So every hour, half the air in the house to upwards to maybe even a whole entire volume of the house gets exchanged. So all that cold air comes in, has to get heated up, and then it goes out. And so the more leakage you have in the house, of course, the more energy you've got to put in the house to keep the house comfortable. And the more uncomfortable the house is, basically, because you got cold air coming in all kinds of places. This house is tight to the point where it has only 1/10, actually a little less than 1/10 of an air change per hour. So the air can get pretty stale. And in this house here, where I've been fairly careful with material selection, it's not chemically stale, it's moisture. So moisture could build up in this house to the point where it would start to condense on windows and start to be an issue. So this helps eliminate that problem too, because it's always ventilating the stale, moist air out, bringing in dry air from outside. But the air coming in, of course, gets warmed up by the air going out, and so you don't have cold air blowing in the house. The other thing I did with this is I had the intake, the stale air going out through this port here, which is in the basement. So basically my basement air gets pulled out, goes through the heat exchanger, out, cold air comes in and goes upstairs into the house. So the air movement in the house this is called a balanced system, so it's not pressurizing or depressurizing parts of the house. It's just simply supplying air to the upstairs, and then the air gets drawn out down here. So the air moves down through the house, so all the stale air in the house gets pulled down into the basement, goes out of the basement, along with radon gas in the basement. And so this house had radon gas levels of about 4.2 picocuries per liter. Picocurie is a measurement of radioactive measurement, and 4 picocuries, 4.2 is above the standard. The standard in the U.S. is 4 picocuries per liter, and European standard is 2 picocuries per liter. So we were at 4.2. So I put this unit in, pulling air out of the basement, which drops the radon level to about 1.9. So I dropped it to a much safer level just by simply operating my exchanger. Now in the summertime, of course, the house is opened up, so you don't have to worry about it. But in the wintertime, when you've got the house closed up for many, many months, radon levels get to be a problem, and this is one way to alleviate it. We also did this, Teresa Jones, who's one of the instructors out at GCC, she had also the same situation, a little bit high radon level in the house, and we did the same thing, put a ventilator in the basement, this same setup, and it eliminated her problem as well. So it's kind of a nice, simple way to do it.
So you only run it in the heating months?
Yeah, I just run it in the heating months because otherwise the house is, I'm always got the doors and windows open and the fresh air in the house. So
Peter, does radon coming in through the bottom here, even though you have it all covered, there are no cracks, no openings in the ground?
Well, again, radon is, can get in through all sorts of little gaps and spaces, even though you think you've got it sealed up. That crack in the floor, there's a crack in the floor right there. That it can get around the foam and then get up through. It's like water in a boat, the water can get in through a tiny crack somewhere way over there and leak in. And so you really do have to make sure that if you have an issue, and again, it's very easy to measure whether you've got radon issues in the house. And if you do have them, the simplest way sealing up certainly will help it. If you've got a real high level in the basement, just sealing up all the cracks around the edge will definitely help drop the level. But you may not be able to get it down to a safe level without some sort of remediation effort. Now you can also see, here's a great example here.
Yeah.
This is sealing the rim joist.
Yep.
So you can see it's kind of funky looking stuff, but they just come in here with a gun and.
Is that the two-part? What do you use?
That's a 2-part spray foam.
Okay.
I used Thermal House from up in, now they're in Brattleboro.
Oh.
Yeah, and they use the bio-based foam, which is partially soybean oil. And so that does a great job of insulating and air sealing. And so that just sort of blended right down onto my foam sheeting that I had on here.
So you did the foam first,
Yeah, I had the foam on, all the foam was in place first.
and then I had this.
And then I had that done later on, actually a year or two later.
And what's the factor, the R factor for the foam?
About R6 per inch. So the thickness varies, but it's nominally about 3 to 4 inches on the rim joist.
And do you need to cover it with some kind of fire rating, the blue and the...
Well, it depends on what your building inspector says, but Jim Hawkins here hasn't really said much about this. But typically, when you put foam up on a wall, you want to put a fire retardant surface on it. In this case here, it would be sheetrock. But until I'm told to do it,
Okay.
again, there's no real flame sources down here. They got to ignite that.
Exactly.
And it doesn't exactly explode into flame either. I mean, it's one of these things where you, if I was down here doing, welding and some sort of a thing that used a lot of flame and stuff, I'd be concerned with it. But it's pretty benign material just sitting here like this. They do have, again, the thing with these fire retardants is they have this intermittent coating, which basically does anybody here old enough to remember the little dark gray black tablets that you could put down and put a match onto, and they would ignite and make a snake.
Oh, yeah.
Yeah. So that type of material, they have actually coatings that you can coat foam materials with, and if they get struck by high heat, they foam up about a ½ inch thick, and they create a fireproof barrier, a fire retardant barrier. But it's specifically matched to the foam. So, like if you have a certain product that you're foaming with, it has a specific coating that can only be used with it. So it's all it's one of these things where they only test it with that material. It has to be a certain thickness and everything else. So the only other way to do it is just put sheetrock on it, and the sheetrock will protect it. So that's, again, the thing with sheetrock is that you'd have to attach it with something, and probably the simplest way to attach it would be to put a shoe down here and put a 2x4 up flat against there, secure it up top, and then screw the sheetrock to the 2x4. That'd be the simplest way to do it. And that wouldn't take too long, but it would be a tedious process.
Tough getting the sheetrock down your.
You come down at 3 foot wide sheets. Well, actually, you can take that stairway. I have actually got 4 footers down here. You can take that stairway out. No.
Oh, you can?
Yeah, that can be removed.
Now, is it hard to decide to make this a 4 foot high?
No, I hate basements.
Because you're so tall. I mean, you're so tall.
I hate basements. Basements are one of those areas that just, you just collect junk in it that you don't really need, and most basements are old, moldy, and wet. And, I just moved this box over here. It was over here. I moved it over there. That's been sitting there for 2 years. It's bone dry. It's just so different to have a basement like this. But I mean, again, it's just storage down here. I do have some mechanical equipment down here. The solar hot water system. You take a look at that over here.
Right.
Bicycle built for two, but
I love that Peter's garage is for the bicycles.
Well, one side is for Chris's car, but the elf. I took the elf down to Building Energy and I brought it back, and it's got a box fell on it and cracked the top plastic. I got to fix it, so that's been sort of taking up the space at the moment. But this is the hot water system, solar hot water system, and this uses a standard electric hot water tank and a flat plate heat exchanger. So this is the heat exchanger that gets the solar fluid transferred into the potable water. So I have a standard old electric hot water heater back there, which has an electric element in it that's the backup heating, which is turned off basically. I never use it, but it's there. And so this pump here circulates fresh water from the tank through the heat exchanger. This pump over here circulates the solar fluid through the collector and back through the heat exchanger and then back out again. And both pumps will come on when the controller here tells it to. This is a little Arctech controller made by a fellow over in Maine. And this shows you right now, it's showing the collectors at 75 degrees and the storage tanks at 72. And it won't turn on until there's about a 5-degree temperature difference. So this isn't going to start to circulate until the collectors out there get a little bit warmer. Again, those collectors take a little bit longer to warm up than the hot air collector because they're out there in the breeze and they've got a lot of mass to them. So they'll take a little bit to warm up. So this circulates, and when the temperature gets up to, let's see, I've got this set at 9 right now. This is the diverter valve. This is just a little thermal valve that fluid flows through it. Depending on where you have this adjusted, it will open another circuit. Well, the other circuit is basically going into the heating system. So you can see I've got the valves open for this to go that way. And then it returns from this one, connects back in. So if the temperature gets hot enough in the tank to get this valve to open, this circulating pump just starts to push the fluid through the heating system. So this little pump run by those panels out there will help heat the house as well. But otherwise I would have basically probably just a strip of baseboard hot water running around here and coming back in. That would be the heat dissipator if for the winter period. Because again, in the winter, this thing can put out enough heat to actually overheat the tank. So even in the dead of winter. And these, you have a pressure gauge.
Now,
here that tells you
that's
the
all
system.
automatic though, so that you don't have to worry about running down here and guessing when
No.
it's overheating?
Oh, no, this just does it. This is fully automatic thermal valve. So it just does its thing. And I just in the winter I set it up to the high temp. In the winter I set it down to a low temperature to start diverting. In the summer I set it up high.
Did you say in the winter you have to worry about it overheating?
It can it can. Up, see, look, it got to 76 in the collector.
More than in the summer?
No, more in the summer. But in the winter I still have to be concerned with it overheating because it's such a big system out there.
Yeah.
Again, those 3 collectors are out there because we had those on our building over in Maine when I had my solar business over there. We had them on the building over there, and my partner never got them going. And so one time he wanted me to do some engineering for him, and I said, hey, well, I'll take the solar collectors and trade for the engineering time. So I had 3 collectors, so I put them up. Like I say, I only really need 1. But,
And you said you cover up some
I
of
just
them.
I have a tarp. I just put a tarp over 2 of the collectors for the summertime. But it's interesting. I mean, solar thermal systems. It's like you've always got hot water. It's even like today, it's heating water. So it will. Oops, up to 86. It must have gotten a little brighter outside.
Yeah, it is.
Yeah. Oh yeah. Look at it, it's coming up real quick now. But the other way to do this, and again, this is only because solar photovoltaics have gotten so expensive. I mean, this is an old technology. I mean, look at all the copper piping, all the fluids, no matter how good, I always get leaks. It's like impossible. They don't leak much, but I mean, there's always little tiny leaks. It's like, this is so irritating. So with photovoltaics now, we can take an electric hot water tank, like that one right there, and change the element to a 120 volt element, put up 5 solar panels, solar electric panels, and use a small converter device. It's a special PowerPoint tracking device like these big utility inverters have in them. And I can just have my PVs directly heat the hot water. No fluids, no copper pipes, no nothing. It's a little different technology, but it should work. I've got a prototype I'm putting together. So you wouldn't need any of this. You would just simply have the electric photovoltaics heating the water. And then, of course, if the tank's all fully heated up, it just turns off. Automatically flips off the switch, and nothing overheats, and nothing happens. It just shuts off. So that's another way to do it, and I think it might be the future. Again, with the photovoltaics getting so expensive, the only difference is that you need much more space because the photovoltaics are less efficient in converting that solar energy into heat. A hot water system can do it at 30 to 40% efficiency and over the year, and the PV will only do it at about 15%. So you need about 3 times the area to cover. Cost is about the same, but
You could combine your PV with one of those heat pump water heaters, maybe.
yeah, but the heat pump water heaters are kind of tricky in New England because you put it in your basement and you end up chilling your basement. The heat's got to come from somewhere.
Yeah.
Down south they work great, but in New England you don't really want to use them in the winter because the space they're in typically you're having to heat somehow. So it ends up being a situation where you turn on your oil burner to make your hot water through your heat pump. I mean, they put one down at the library down here. The electric bill went quite a bit up.
Wow. Peter, is it still true that the incentives for solar are going away next year?
Well, the incentives in Massachusetts are gone. I mean, basically now it's just a loan program for a low interest loan program, or half your interest they'll reimburse you, but you have to be low income and there's a bunch of other things on it. So that's the incentive at the moment. But again, the cost of PV has come down so much that I guess that's what they were saying is it's really unnecessary. But the federal will be around until 2016. You'll be able to take the credits. I think even in you'll be able to, any extra credit you have, you can apply to probably one more year after that.
I thought you got to use them for 20 years.
No, your federal tax credits. These are federal tax credits.
Yeah.
Federal tax credits. If you put a system in like last year, it cost you $10,000. You'd have a $3,000 federal tax credit to apply to last year's taxes, 2014 taxes, and you could carry any excess forward 1 year. You can carry it forward 1 year.
I thought it was 20 years.
Not the tax credit. Tax credit can only be carried forward 1 year.
Huh.
So you have to make sure that you make your income sizable enough to use it by taking out. I guess in my case, I got to take out enough retirement to make it worthwhile. You hate to lose that credit.
Yeah.
I got a question. So if you take 5 PV panels to run that system,
Yeah.
do you lose that through the SREC program because now you're just sending it directly to a...
Yeah, it's totally separated.
Yeah,
And again, the reason I like to do separate systems is because you get much more reliability that way. In other words, if you have a system that's completely independent of the utility, you never have any problems with in a case like this, you never have any problems with overheating and stuff, where most systems are set up to run on utility power. The utility interface systems, you could say, okay, let's just oversize the utility interface array and have that directly feed a regular hot water tank. And what I like about the independent system is you don't have any load on the utility. Again, I'm always thinking about what am I loading the utility with? And of course, we as a whole civilization have to think about how are we loading our utilities, because the utilities have to have all that generation sitting there waiting for you to do it. So I try to get my systems off the utility as much as possible so they don't have the impact. That's why electric stoves, I don't really like electric stoves because you kick on that oven and a few top burners and you're pulling a lot of wattage from the utility. The utility has to supply that, so it has to have generation sitting around waiting for you to do that. So if all of us could reduce our electrical peak loads, these big heavy peak load users, it's beneficial to all of us and the utilities. And a hot water heater, electric hot water heater, is a big peak load. It kicks on with as much as sometimes 5,000 watts or so. So it can be a hard load for the utility to deal with. So I try to keep as many of these separate as possible. But yeah, you're right. If once the hot water's hot, then your electricity's going nowhere.
No, my question was, you don't get an SREC for doing it that way because you're going directly...
Oh, you can't get an SREC because you haven't got any record of the generation.
Right. So,
But SRECs are kind of a...
I'm sorry, what is that?
SRECs are Solar Renewable Energy Credit. The SRECs, one of the big programs in Massachusetts was you basically put in a system and then you could not only get net metering, but then you could sell your credits, your clean energy credits, to a utility who has to have a certain amount of their portfolio in clean energy. The problem is that you end up having all these houses with solar electricity, and they really don't have solar electricity. The utility has solar electricity. So in a way, you're sort of giving the utilities a cheap way out of doing what they should be doing, putting in their own generation, clean generation, not simply buying it from somebody else, but putting in their own generation. So it's, I mean, the SREX program is great for getting people to put solar in, but the utilities would have had to do it their own anyways, and then you would have had double the amount of solar out there. You know, people would have still put their own solar in unless they were strictly, I mean, again, I really wish people would put solar in because it's good for the environment and good for our future rather than just, oh, it's a great economic, benefit. We really have to get over this idea that everything we have to do is going to make us money, because solar is the only way we're going to save our butts from global warming. And I mean, that's an end game. We're done. We're cooked. So if we don't start getting on board saying, I'm going to take that money that I was going to use to go on a big fancy vacation, and I'm going to go buy some solar panels and put it on my roof because it's good for my grandchildren and my children and the rest of the world, that's where we got to get to. Not, oh, can I make money with this? I mean, if you make money with it, great, but I mean, it's first and foremost, we got to do it for the environment that we're killing very quickly by doing everything we're doing the wrong way. So SREX, it's an interesting program. It's got a lot of solar up.
And it's allowed people that couldn't otherwise afford it to do it.
Right, but the thing is, I wish they'd get some programs, like we've had a program for solar hot water systems where you can get a no-interest loan for 7 years for up to $25,000 through Mass Save to do solar thermal. Why can't we extend that to
PV.
solar
that makes
electric?
a lot of
Exactly.
And then people can, people of less, this program they got right now, which is this loan program, give you half your interest back, it doesn't do anything for anybody with limited income. It's ridiculous. So, the other program, the program that gives you the no interest loan for 25 years, you can have you can have basically no income, and if you can get the loan, you can put in the system and it'll save you money day one. Start saving you money by basically giving you electricity less expensively than what you're gonna, the cost of the electricity, the amount of electricity you save, the value of that is gonna be a little bit more than what the loan's gonna cost you. And I mean, that's a great program, but they won't extend it to PV. They're doing this other weird program with $30 million backing it. I don't know where the money's going to go because I don't think many people are going to use the program. So that money's just going to sit around, I guess. When it could be doing something much better. But no, we got to get more PV out there, and more. Again, the neat thing about the smart grid is that you can't, obviously, if everybody had photovoltaics on their house, you wouldn't have a grid that could operate because everybody would be generating photovoltaics, getting net metering, and the utility would basically be sitting there going, what am I doing here? All I'm doing is acting as a conduit to move electricity around. And so you really do need to have a smart system where you can use houses as energy storage. Again, like a refrigerator is an energy storage device, a hot water heater is an energy storage device. As you can use electric vehicles in the future will be storage devices. So you can start to get a situation where the smart grid can basically manage loads. If I have 10 people with electric hot water heaters and I basically can cascade them up and down so that only one electric hot water heater is on at any one time, all of a sudden I've totally changed the way the grid operates. And I can do that by just simply turning this one on for 10 minutes and all these are off for a short period of time, then this one comes on, this one comes on, this one comes on, and a smart meter can do that, smart metering system can do that. So you can actually start to have a much more uniform load, which the utility really performs well with, very uniform loads. It's the big peak loads that are all a big killer. And that was interesting, they've got they're thinking of basically valuing electricity from photovoltaic systems depending on which way they face. If you have a solar system facing west, it produces all its max power in the afternoon, late afternoon, when all the loads go way up. So that electricity is actually worth much more than electricity from one facing south.
Huh.
So it's time of day loading. But if we can get more and more of this storage via different means, that can help level out the peaks and lows and make it better for everybody, including the utilities. But
Eat local. Heat local.
Eat local, heat local. There you go. Yeah, yeah. I mean that south-facing window certainly is a great way to warm up a house. And it's coming. That delivery's coming right in there from 93 million miles away.
Reduce, reuse, recycle. I want to say it again. Reduce, reuse, recycle. We gotta watch what we buy. What's it contained in? What's it contained? Where will it end up? Where will it lie? Can it be changed and used over again? Reduce, reuse, recycle. I wanna hear you say reduce, reuse, recycle.